the deadly shadows. For decades, we were told the moon was a silent rock, lifeless and barren. But inside its deepest craters, hidden where the sun never shines, scientists have discovered something that changes everything: water ice. These frozen reserves could become the fuel of rockets, the oxygen for astronauts, and the very foundation of a human colony on the moon. It should have been humanity's greatest discovery. Instead, it may be our deadliest trap, because those same craters that hide the water also hide something else. An invisible force building in the dark, waiting to strike. A force that can fry machines, suffocate habitats, and even kill the astronauts who dare to step inside. And here is the chilling truth: the most dangerous place on the moon is where the water is. A silent frontier. To understand why, you must first understand the geography of the moon. Unlike Earth, the moon tilts only slightly on its axis. This means that at the lunar poles, sunlight never reaches certain places. Vast craters near the north and south poles are walled off from light by their steep rims. Inside, the floors are locked in eternal darkness. These places are called permanently shadowed regions, or PSRs. For billions of years, they have sat in black silence, their temperatures falling below 200 degrees Celsius. That's colder than Pluto, colder than the outer planets, colder than anything nature creates on Earth. These places are so dark that no human eye could adjust to see their depth. They are not simply dark, they are black voids carved into rock. Yet inside these voids, ice glitters beneath the dust. Ancient, untouched, locked away in a natural freezer since the birth of the solar system. To scientists, that ice is treasure. It can be melted into water, split into oxygen to breathe, separated into hydrogen to make rocket fuel. With it, humanity could leap beyond Earth, staging missions to Mars and even further. But every treasure comes with a curse. And the curse of the lunar poles is hidden electricity. A hidden battery. The moon has no atmosphere, no magnetic shield. Every second, it is bombarded by the solar wind, a stream of charged particles blasted out by the sun. These particles are mostly electrons and protons. But electrons are lighter, faster, and far more mobile. When the solar wind hits the moon, electrons stream across the surface. In sunlit regions, some are kicked back into space by photons, balancing the charge. But in the shadowed regions, inside those eternal craters, there is no sunlight to bleed the electrons away. So they build, slowly, silently, relentlessly. Over time, the craters become giant invisible batteries, floors coated with negative charge. The surrounding sunlit terrain, shedding electrons, becomes positively charged. Between the light and the dark lies a razor-thin frontier of electrical tension. Step into it with a metal suit. Roll into it with a rover. Drill into it with a machine, and you may complete the circuit. And when that circuit closes, the crater discharges in a sudden, violent spark. No warning, no sound. Just a flash of electricity powerful enough to fry sensitive electronics, cripple life support systems, or send a jolt through a human body that is already vulnerable in the vacuum of space. A nightmare scenario. Imagine it. A crew of astronauts lands near the rim of Shackleton Crater at the moon's south pole. Their mission: to explore the floor where radar data suggests thick sheets of ice lie buried in the soil. They prepare carefully. Suits are checked. Rovers are powered. Sensors hum in the thin silence of the lunar surface. Step by step, one astronaut begins the descent into the shadow. Their helmet light cuts only a few feet into the abyss, swallowed by the black. The suit is designed to withstand radiation, micrometeoroids, and extremes of cold. But no suit can change the fact that it is, electrically, an isolated shell in a charged environment. The astronaut kneels to scoop a sample. Static builds invisibly across the fabric. Then, without warning, a spark leaps across the backpack unit, discharging into a connector at the life support system. Inside the helmet, alarms scream. Oxygen flow wavers. For a split second, the astronaut doesn't know if their air has failed. Their breathing spikes, fogging the visor. The radio crackles, cutting in and out, leaving the crew above the rim in stunned silence. It lasts only a moment, but it is enough. Enough to end a mission. Enough to take a life. That is the nightmare of the permanently shadowed regions. Not the cold. Not the darkness. But the invisible trap of electricity, primed for anyone who dares to enter. Why shadows kill on Earth? Static electricity is harmless. Rub your socks on a carpet, touch a doorknob, and you feel a tiny shock. But the air around you bleeds most of the charge away. Our atmosphere is a constant discharge valve. On the Moon, there is no such protection. The vacuum holds the charge in place. The only release is through arcs of electricity, sudden discharges that leap across gaps like lightning bolts in miniature. And the longer a crater sits in darkness, the more the charge builds. Researchers running computer simulations found that voltages in these craters could reach hundreds or even thousands of volts. Enough to fry sensors, enough to short out motors, enough to endanger a human heart if the current found its way through a suit's life systems. And then comes the second danger: dust. Dust that cuts like glass. The surface of the Moon is covered in regolith, fine jagged dust formed by billions of years of impacts. Unlike Earth's sands, which are smoothed by wind and water, lunar dust is razor-sharp, each grain edged like a shard of glass. Apollo astronauts hated it. It shredded their gloves. It jammed zippers. It stuck to everything and refused to come off. They coughed when it leaked into the cabin, describing it as smelling like gunpowder. Now add electricity. In a shadowed crater, the regolith grains become charged. They cling harder than ever, embedding in seals and filters, coating visors and smothering solar panels. Worse, charged grains can actually levitate, floating above the ground in eerie clouds. A single step may send a mist of electrified dust rising to choke intakes, blind cameras, and clog instruments. If such dust ever entered a lunar habitat, it could slice into lungs the way inhaled glass would on Earth. It could jam valves in oxygen systems. It could ruin an entire mission in hours. The Moon, it turns out, has weapons we never imagined, hidden in the very places we must go to survive. Treasure and trap, here lies the paradox. Humanity cannot expand into space without water. It is the resource more valuable than gold, more vital than fuel, and the Moon's poles hold it in abundance. But those same poles are places of eternal shadow, eternal cold, and eternal danger. They are the most hostile environments in the solar system, where dust and electricity form an invisible gauntlet. It is as if the Moon itself set a price for its treasure. Water can be yours, but only if you risk the shadows. For every step deeper into those pits, astronauts will gamble against silence, cold, dust, and hidden arcs of electricity. And the question is not just whether we can survive it, but whether the price will be too high to pay. Because if we cannot safely enter those shadows, then the dream of building a base on the Moon may collapse before it even begins. The shocking trap, the shadows of the Moon, are not just empty spaces. They are machines of physics, silent engines that twist the laws of electricity against us. To step inside one is not to walk into darkness. It is to walk into a trap that has been charging for billions of years. And the trap begins with the solar wind. How the trap is built: the sun is not gentle. Every second, it hurls a storm of particles outward into the solar system. This storm, called the solar wind, is made of two key players: electrons and ions. Electrons are tiny, light, and fast. Ions are heavier and slower. When this invisible storm strikes the airless surface of the Moon, the electrons win the race. They pour into every shadow, slipping into the depths of craters where sunlight never follows. On the bright side of the Moon, photoelectric reactions kick electrons free, balancing the charge. But inside the darkness, there is no sun to counter them. So the electrons pile up, clinging to the regolith, coating every grain of dust with negative charge. Meanwhile, the heavy ions lag behind, leaving the floor of each crater imbalanced, an island of negative energy surrounded by slightly positive terrain. What does this mean in practice? It means that every shadow becomes a giant invisible capacitor, storing energy that waits only for one thing: a path to escape. and that path may come in the form of a human boot, a rover's drill, or the metal edge of a solar panel lowered into the dark. Sparks in the void on Earth. Sparks are trivial. Walk across a carpet, touch a doorknob, and the shock is forgotten instantly. But on the Moon, without air to bleed charge, the spark can grow. Computer models have shown that voltages inside permanently shadowed craters can rise to hundreds, even thousands of volts, enough to arc across small gaps, enough to jump through the delicate circuits of a rover or a lander, enough to surge into a spacesuit and knock out critical systems. There is no sound in the vacuum. You would not hear the snap, but you would see the flash, a silent blue arc cutting across the black. One spark could erase memory banks, corrupt navigation software, or render life support pumps useless. For machines designed with only narrow margins of safety, one uncontrolled discharge could mean complete mission failure. And for humans, the risk is worse: a spark striking across a connector on a life support pack or jumping into an oxygen regulator is not just inconvenient, it is fatal. The dust factor, but electricity is only half the trap. The other half is dust. Lunar regolith is no ordinary dust. It is jagged, sharp, and microscopic, a powder made of shattered glass like particles. It clings to everything it touches: gloves, visors, seals. Apollo astronauts cursed it, calling it the biggest nuisance of their missions. Now imagine that dust charged like static balloons. Every step, every wheel, every drill into the soil adds triboelectric charging, the same principle as rubbing a balloon on your hair. Dust grains scrape against each other, trading charge. But unlike on Earth, there is no moisture in the air to bleed this charge away, so the particles hold it. Each becomes a tiny capacitor, and together they form an electrified cloud. This means dust does not just cling, it attacks. It creeps into bearings, where sparks leap between grains, welding them into place. It coats solar panels, reducing efficiency to 0 in hours. It floats above the ground, forming shimmering, invisible fogs that short out exposed instruments. And once inside a habitat, it scars lungs like microscopic blades of glass, embedding charge into tissue where it can't be removed. The Moon is often pictured as silent and still. But in these traps of shadow, the very soil becomes alive with electricity, reaching for every machine and every human who dares to enter. A mission in peril. Picture this: a robotic rover is deployed near the rim of a polar crater. Its mission: drill beneath the regolith and confirm how much ice is hidden below. Engineers on Earth watch nervously as the auger spins down into the soil. At first, the drill cuts clean. Samples are collected. Data streams back. Then the unexpected happens. Charged dust begins to cling to the drill's metal flutes. Each grain locks into the next, forming a growing mass that refuses to clear. Rotation becomes harder. The motor strains. Heat builds in the housing. Then the discharges begin. Sparks jump from the drill into its own casing, tripping protective circuits. Sensors flicker. The rover's computer, flooded by static, reboots mid-operation. When the signal returns, the drill is jammed solid. The rover is crippled, its primary mission lost. Millions of dollars and months of planning destroyed in a single hour, not by impact, not by radiation, but by invisible electricity and dust. Now imagine this same scenario, not with a rover, but with a human. A spacesuit knee deep in regolith. A gloved hand gripping a charged tool, a jolt leaping through connectors into the life support unit. The astronaut feels their chest tighten, not knowing whether it is fear or oxygen deprivation. Their crewmates can only listen to broken static on the radio as precious minutes slip away. That is the shocking trap of the lunar shadows. The physics of fear scientists call this effect differential charging. But to an astronaut, it will feel like betrayal. The very ground beneath them will resist their presence, holding silent energy until it finds a way to release. In controlled lab tests, simulations show that arcs could jump across gaps of several millimeters, enough to cross connectors, enough to leap through unshielded equipment, enough to ignite a spark in a sealed oxygen system, something every astronaut fears above all else. The most dangerous aspect is not the spark itself. It is the unpredictability. A machine may work for hours and then fail in an instant. A suit may seem safe and then flash with blue fire at the worst possible moment. There will be no warning labels in the craters. Only silence, waiting to strike. Shadows of strategy. How do you fight an enemy you cannot see? Engineers are working on solutions, but none are simple. Spacesuits may need conductive threads woven into their outer layers to spread charge evenly. Boots may include grounding strips that discharge energy step by step. Machines may deploy tall grounding masts before entering a crater, giving electrons a controlled path to escape. But every safeguard adds weight. Every new design consumes power. Every precaution slows the mission. The moon's shadows do not just threaten safety. They threaten the very feasibility of exploration by making everything harder, slower, and more expensive. Some mission planners are already considering compromise. Avoid the deepest craters altogether. Target only the fringe zones, where sunlight can provide power and charge is less severe. Collect smaller amounts of ice mixed with dust, instead of plunging into the richest, darkest deposits. But such compromise comes at a cost. Less water means fewer resources. Fewer resources mean higher dependence on Earth. And dependence on Earth may mean that humanity's dream of a true lunar colony never becomes reality. The trap that guards the treasure, the shocking trap of the moon, is no accident. It is the product of physics itself. Charged particles, eternal shadows, and dust sharpened into knives. It is as though the moon has hidden its treasure behind an electric fence, daring us to reach through. The ice is there, waiting. Enough to build a city. Enough to fuel a fleet of rockets. Enough to change our future forever. But every step into the shadows risks disaster. Every machine that rolls into the dark may never roll back out. Every astronaut who enters may walk straight into the trap that has been waiting since the first light of the sun. The question is no longer whether water exists on the moon. The question is whether we can survive long enough to use it. Because in the shadows, survival is never guaranteed. The truth about lunar water: for most of the 20th century, the moon was believed to be a dead desert. Apollo astronauts carried back rocks that seemed bone dry. Instruments detected no atmosphere, no magnetic shield, nothing that could protect water from evaporating into the void. The conclusion seemed absolute: there was no water on the moon. But history has a way of punishing certainty, because what we thought was a barren wasteland turned out to be hiding one of the greatest surprises in the history of space exploration. The moon was not dry at all. It was a world laced with secrets. Molecules of water hiding in the soil, crystals holding ancient ice, and shadowed craters filled with frozen reserves that could change humanity's future. The revelation of lunar water did not come all at once. It came in whispers, hints, and then in a sudden explosion of truth that forced us to rewrite everything we thought we knew. The first hints, the first clues, came in the 1990s, decades after Apollo. Orbiters carrying radar instruments passed over the moon's poles and detected strange reflections. Signals bounced back as if they were striking something rich in hydrogen. Hydrogen can mean many things. But to scientists, it raised one thrilling possibility: ice. Could it be that, in the deepest shadows of the lunar poles, ice had survived, untouched for billions of years? Could those craters be more than dark pits? Could they be natural vaults, protecting water in the coldest conditions the solar system can create? The idea was controversial. Hydrogen could come from other sources, solar wind, or trapped minerals. Radar echoes can deceive. For years, scientists argued, was it real or was it just noise? The moon seemed to laugh at us, offering just enough evidence to tempt, but not enough to confirm. The game changer then came the late 1990s. NASA's Lunar Prospector orbiter mapped hydrogen concentrations across both poles. The data was clear. Large quantities of hydrogen were clustered exactly where the shadows were deepest. Scientists called these regions cold traps. places where molecules of water could fall and never escape. Still, skeptics remained. Remote sensing could not tell us if the hydrogen was locked in true ice or just scattered atoms bound to dust. The moon remained a riddle. Until 2009. That year, NASA launched a mission designed to answer the question once and for all. It was called LCROS, and its plan was as audacious as it was simple: throw a spacecraft into the moon and see what comes out. LCROS targeted a crater near the South Pole. A spent rocket stage slammed into the darkness at over 9,000 kilometers per hour. The impact blasted a plume of debris high above the rim, where trailing instruments could analyze the cloud. When the data arrived, the answer was unmistakable. Inside the plume were signatures of water ice. The moon had revealed its secret with a violent whisper. For the first time, humanity knew with certainty there was water on the moon. Not theory, not rumor, proof. A world rewritten. The discovery triggered a scientific revolution. Suddenly, the old image of the moon as a sterile desert collapsed. New missions poured over the data. India's Chandrayaan-1 orbiter detected hydroxyl molecules and water signatures across the surface, even in sunlit regions. Water was not just hiding in the shadows. It was woven into the very skin of the moon. How could this be? How could a world blasted by radiation, baked by sunlight, and stripped of atmosphere hold water at all? The answer was even stranger than the question. Every second, the solar wind bombards the moon with protons. When these protons strike oxygen atoms in lunar minerals, they form hydroxyl groups. Some of those hydroxyl molecules combine further to make water. It meant that the moon was not just passively holding ancient ice. It was actively creating water, not in oceans or rivers, but in invisible cycles across the dust, appearing and vanishing with the rising sun. What we thought was dead had become dynamic. The moon was alive with chemistry. The smoking gun in 2020, China's Chang'e 5 mission returned samples of lunar soil from the Oceanus Procellarum region. Scientists carefully examined the grains under modern instruments. Inside them, they found measurable amounts of water. Tiny, but undeniable, some locked in glass beads formed by ancient impacts. Others bonded to minerals. Even more shocking, when Apollo rocks were re-examined with 21st-century equipment, traces of water were found in places no one had expected. The samples we once believed bone dry were in fact hiding a secret all along. The moon had been keeping water not just in craters, but in beads, in crystals, in minerals scattered across its entire face. This was not a dead rock. It was a reservoir. Why water matters, but why does this matter? Why is water on the moon more than a scientific curiosity? Because in space, water is life itself. With water, astronauts can drink, grow food, and breathe. More importantly, water can be broken into hydrogen and oxygen, the two ingredients of rocket fuel. If we can harvest lunar ice, the moon becomes more than a destination. It becomes a refueling station. Instead of launching everything from Earth, missions could mine water on the moon, turn it into fuel, and stage voyages to Mars, Jupiter, or beyond. The cost of space travel would collapse. Entire strategies of exploration would change. The moon would no longer be a barren outpost. It would be the first step of a permanent human presence in the solar system. That is the dream. And that is why the discovery of lunar water was celebrated as one of the most important scientific revelations in modern history. But the dream comes with a shadow, because the richest ice lies not in easy plains, but in the permanently shadowed craters. The same places we now know are electrically dangerous, dust-choked, and colder than anything humans have ever faced. The treasure and the trap are one. A new mystery, the revelation of lunar water, also raises a deeper question. If the moon can hold water, if it can even create it under the right conditions, how much more might we find? How much might be hidden in places we have not yet explored? And what does it mean for our understanding of the solar system? Was water always here, seeded by comets and asteroids in the ancient past? Or was it born from the chemistry of dust and sunlight, a process that may exist across worlds we once dismissed as sterile. Each discovery on the moon rewrites not just its history, but the history of water across the cosmos. The dual face of the moon, the truth about lunar water, is this: the moon is not dead. It is a world that carries scars of fire and ice, a world where shadows guard frozen vaults and sunlight sparks chemical reactions across the soil. It is both a gift and a warning, a place where our greatest hope for expansion collides with our greatest technical challenge. Because water is there. We know that now. The question is not whether it exists. The question is whether we can claim it without destroying ourselves in the attempt. And that is the paradox. The moon offers us the very resource that could make us a spacefaring species, but it demands that we risk everything to retrieve it. What was once thought of as a dead rock has become the most contested prize in human history. But if the moon has already betrayed our certainty once, what other secrets does it hold? And how far are we willing to go into the shadows to find them? Survival or collapse? The discovery of water on the moon was hailed as humanity's greatest hope. But every discovery carries its price, and the moon's price may be higher than we can pay. Because finding the ice is only the first step. The true challenge is surviving long enough to use it. The question is no longer, is there water? We know it's there. The question is, can we take it, or will the attempt destroy us? The engineering nightmare on paper. The process sounds simple. Land near a shadowed crater. Drill into the regolith. Heat the soil until the ice trapped inside vaporizes. Capture the vapor, cool it, and store it as water. But nothing on the moon is simple. First, the temperature. In permanently shadowed craters, the cold plunges to 200 degrees C, colder than liquid nitrogen, colder than the surface of Pluto. Machines that work perfectly on Earth seize up instantly in such extremes. Lubricants freeze. Metals grow brittle. Electronics fail. Then comes the dust. Razor-sharp, abrasive, and electrically charged, it clings to every moving part. Bearings grind. Motors stall. Filters clog. What was once a drill becomes a tomb for itself, jammed solid by dust that refuses to be cleared. Add to this the invisible storm of electricity. Every wheel, every tool, every step builds charge until it arcs in a flash that can wipe memory banks, corrupt circuits, or trigger a catastrophic failure in life support systems. What looks like a routine operation in an engineering diagram becomes a gauntlet of hazards in the lunar dark. A mission scenario: imagine a future mission to Shackleton Crater. A robotic lander sets down near the rim, where sunlight still grazes the surface. Engineers deploy a rover designed for one purpose: to drill deep into the shadows and bring back ice samples.